So if you remember, we covered all the forces that are going through the vehicle, and the last bit was around about drivetrain. Okay, when you start applying some tractive forces to the vehicle, the loads and stuff start to change. Okay, but what I want to do here is just I've given you a typical torque, power, and fuel consumption curves for gasoline, so petrol and diesel, so spark ignition and compression ignition engines. Okay, you've been covering this stuff in advanced, emerging automotive technology, I'm sure. So obviously here we've got a gasoline engine with a power or torque curve. It looks like this, okay, and the power curve up like that, okay, and you can see the power relates to this side, torque is in this side, power is in kilowatts, torque to Newton meters, okay. And then obviously you've got a fuel consumption, specific fuel consumption curve, which is in kilograms per kilowatt hour. Okay, so it's a time related thing, because obviously the hours is time. Okay, and it's specific, so you can compare various things together, and you can see that obviously with the diesel engine, these numbers are smaller than these numbers. Okay, you can see there's the efficiency. Diesel gives a much flatter torque curve, which gives a much more linear power curve. Okay, and you can see that's a typical diesel engine. And obviously these curves are also generated when you're at maximum torque power torque output. Okay. So, like I said, engines create torque. Okay, and by multiplying the torque by the engine speed, the units per second, you get power. Okay. That's the other thing that's worth bearing in mind. So, in terms of the tractive force at the wheels, okay, we call that FT. That's the tractive force. Okay. If you want to work out the torque of the wheels, then you take your tractive force and you multiply it by your radius of the wheel. Okay, that makes sense. So we call that torque at the wheel, TW, okay? And torque at the wheel has got to equal torque at the engine, created by the engine, times by the gear ratio, times by efficiency of the drivetrain. Okay, so you can see the things are starting to be related together. So FT times by R is going to be the torque of the wheel, and the torque of the wheel is equal to the torque of the engine through the gear ratio and through some efficiency. Okay, wheel radius, R, torque is generated by the drivetrain, gear ratio. And obviously you can relate to the engine, the speeds also through the gear ratio. So the engine speed is going to be the gear ratio times by the wheel speed. And like I said, so you can get the different speeds available. And that symbol, mu, I think is called, or mu, is the drivetrain efficiency. And you can start to combine these things together. So obviously taking this bit and divided by wheel radius, you get the tractive force as a function of the torque of the engine and the gear ratio. Okay. Now power. Okay, so we've got tractive force in terms of torque of the engine. Power at the wheel, okay, is the torque of the wheel times by the speed of the wheel. Okay. Power is force times velocity, okay, but in a rotational sense, that's going to be torque times by angular velocity. It's TW, okay. TW is TER mu, okay, so that's in here, okay. Okay, but obviously the R's, yeah, that's right. So omega of the engine, obviously that gets rid of the R because we've got the gear ratio in there. Obviously the efficiency, and that must equal the tractive force times by how fast the vehicle is going forward. Okay, dx. Okay, everything's all interconnected, but basically you've got the tractive force. Like I said, it's the wheel torque divided by the radius. So there's your power. Okay, here power divided by omega naught. So that's your power, and you've got your radius in there. Okay, so that's the tractive force in terms of power. And over here we've got the tractive force in terms of power over Vx. Okay, so it's like things are complicated. They're all interconnected together. Okay, hopefully the example that we're about to do is going to talk that out. And so you can work out acceleration in terms of power, how fast the vehicle is going, and the mass of the vehicle. Okay, and obviously power, like I said, you can work it out. So like I said, the problem is it's all interlinked. And which form of these equations you use depends on what you know, okay? So what I thought I'd do is instead of, there is this in-class question, instead of asking you to do it, I thought I'd go through it. It's probably the easiest way we can deal with that. So I'm just going to load this up. Okay, so we're going to do this in class question. So if I, it's a little involved, but it'll be okay. So it says a petrol-driven car with a mass of 1,500 kilograms has a drag coefficient of 0.3 and a front area of 2.16 meters squared. Okay, so you've got the drag details, we've got the mass of the vehicle. The rolling resistance of the tyres with the road surface is 0.01. Okay, so we've got the rolling resistance. When travelling on level ground at 70 miles an hour, work out the tractive force required. Okay, so obviously the tractive force has got to overcome all those resistive forces. Assuming the density of air is 1.225 kilograms per meter cubed, note that 1 mile is 1609. So we'll do part A first, okay? And that's quite straightforward because it covers the stuff we did before. So if I go to here, there it is, there's the question, okay? And if I divide the question up, we'll call this part A and this part B, okay? So for part A, we know that the tractive force, F of T, needs to overcome the aerodynamic, F of A, and the rolling resistance, FRR, okay? And if F of A we know is 1/2 rho CdA V squared, okay, and the rolling resistance is the coefficient of rolling resistance times by the normal force, okay? The road is level, so theta is 0, okay, so we don't have to worry about the grade resistance. We do need to work out V in meters per second, so V is 70 miles an hour, 70 miles per hour. We know in 1 hour you've got 3,600 seconds, and in 1 mile we've got 1,609.344 meters. Okay, and if you do that sum, that's so we've got 1,609.344. Okay, 31.2928. 31. Meters per second, okay? So we can start plugging in some of the numbers. So F of T is going to be 1/2. Rho is 1.225. CD 0.3. A is 2.16. V squared, so that's 31.2928 squared, okay? Plus rolling resistance 0.01 times by the normal force. So that's mg. Because we're on level ground, okay? And so we can work out that the tractive force required is 535.8 newtons. Okay. At 70 miles an hour. Okay. So to overcome the resistive forces, okay, is 535 newtons. That's not a lot, is it? 50 kilograms of weight in a sense, okay? At 70 miles an hour, okay? We're not accelerating the vehicle. Obviously, that's.
If you scroll up to the top, so you can see the full question. Thank you.
Okay. Obviously, that's not to accelerate the vehicle, like I said. That's not going up a hill. Okay, but that's obviously along level ground. To maintain 70 miles an hour, you need 535 newtons to overcome those aerodynamic and rolling resistance forces. Right, so that's part A. Part B Says go on to find the wheel power required at 150 miles per hour, and assuming a drivetrain efficiency of 90%, the required torque generated at the engine. Okay, the gear ratio is 3 to 1, and the wheel radius is 317.45 millimeters. Okay, so part B. Okay, we've got to find the power, which is the tractive force times by your velocity. Okay, at 150 miles an hour. So obviously we can obviously sort out the speed at 100 the meters per second for 150 miles per hour using the same conversion factor. So that's 1609.344 divided by 3600. Okay, and that equals, so if we take 150 we get 67.056 meters per second. Okay, and we know the tractive force. Tractive force is going to be the aerodynamic resistance times by the rolling resistance, okay, times by Vx, or x dot or whatever, okay. And so we can power 1/2 rho CD A Vx squared plus CRRN times by Vx. And so we can plug in the numbers. 1/2 1.225 times by CD, which is 0.3, A 2.16, V squared, so that's 67.056 squared plus 0.3 times by 1500 times by 9.81. No, that's not 0.3. Okay. Times by okay, so we've got, let's work it out. So we've got, so go back, done. 0.5 okay, so 1.1784 we've got 0.01 okay, so we add those together. Five, 3, 5, 4. 5, 3, 6, 5, 4, 7. Okay, so there's the power required at the wheels. Okay, the wheel power, which will be the same as the power required at the engine at 150 miles per hour. Okay. On the so the tractive force is what it says. What did it ask for? It asked for the assuming the drivetrain efficiency of 90%, the required torque generated at the engine. Okay, the gear ratio is 3 to 1. So we know the tractive force F of T is going to be the torque at the engine times by the gear ratio times by the efficiency divided by the wheel radius. Okay, so we can rearrange this equation. Torque at the engine is going to be F of T times by the wheel radius divided by the gear ratio, the efficiency. Okay, and so we've got these numbers, so that's going to be 1. Oh, the tractive force, okay, well that's obviously this bit here, that's F of T. So if I go back and I go back there, 1931.8. Times by the wheel radius, 0.31745, divided by gear ratio, times by the efficiency, 0.9. Okay. So we take that, so we drop that, we take it 0.31745, 0.9 divided by and 3. 227.13 Newton meters. Okay, so it's just about combining the equations together, what you know, okay, and then converting, converting them around algebraic manipulation to get the values you need. So it's quite interesting that a car driving at 150 miles an hour, it only needs 130 horsepower to get there, okay, or to maintain it. Okay? To get there, you might want more, okay, but actually, when a car that's got these characteristics weighs 1.5 tons, has a drag coefficient of 0.3 and a frontal area of 2.16. To actually maintain 150 miles an hour, you only need 130 horsepower, okay? And you only need 230 newton meters of torque to maintain that speed. Okay?